Good morning. Today we will continue with X-ray diffraction. This is very important method for technological and scientific applications. So let me start with the first proposal of diffraction of X-rays from crystals. The proposal made by Max von Laue in 1912, and then just 2 years after his proposal, he was awarded a Nobel Prize because his proposal corrected by experiments. So what was the proposals of von Laue? Two conditions. The first one, if the crystals consist of periodically arranged atoms that act as scattering centers for X-rays. This was the first proposal. And then second proposal, if X-rays are electromagnetic waves with wavelengths approximately on the order of distance between the atoms in the crystal, then diffraction of X-rays from crystals should be possible. So two conditions, two proposals. We consider that crystals are formed from periodically arranged atoms, and the second proposal is that X-rays are electromagnetic waves, but with the wavelengths on the order of distance between the atoms. For example, we are talking about 1 angstrom, 2 angstrom, or something like this in this range. This is the distance between the atoms in many crystals. So then what happened? In the same year, as much as I remember, Friedrich and Knipping carried out experiments to test these proposals. They used this type of setup. Here, there's a crystal, copper sulfide, okay? And there is an X-ray source here. And then X-ray beam is coming. It contains many X-rays. And there is a photographic film here. And they have observed diffracted beams which produced some spots on the photographic film. So this was the first diffraction experiment, and this experiments corrected the proposals of Max von Laue. So then, without any doubt, it was observed that X-rays were diffracted from the crystal and formed spots on the photographic film. So what about the results of these experiments? These experiments proved that X-rays have a wave structure, they are electromagnetic waves, and the atoms in the crystals have a periodic arrangement. So these are the two main results of these experiments done by Friedrich and Knipping. So it was a very important step in history and also in X-ray science. So then, in the same year, in 1912, as we have discussed during the first lecture, father and son Braggs did the analysis of crystal structure by using X-rays. So what they have done, in addition to this analysis, they determined the conditions for the diffraction in a much simpler mathematical expression, which is very famous one, and lambda is equal to 2d sinus theta. And this mathematical expression is much simpler than the mathematical formulation used by von Laue. Okay, so then they determined the crystal structures of sodium chloride, potassium bromide, and also potassium iodide. And this was the first crystal structure determination in the world. So today we know what is the crystal structure of sodium chloride, what is the crystal structure of potassium bromide, okay? We know FCC, BCC, HCP, okay? Many different crystal families, for example, cubic, hexagonal, orthorhombic, okay? But in that date, all this information was missing, okay? And this was very important step in X-ray science. So now let me discuss what is X-ray diffraction? What is the origin of this effect? Here we have a picture. Let's consider that we have a crystal and this black points are the atoms, okay? This is just representation. In a real crystal, of course, atoms are touching to each other, okay? So let me show you here like this. In a real crystal, we have atoms like this. Of course, they have certain distance between the atoms, but they touch each other, okay? If it is a perfect crystal, of course, there is a perfect periodic arrangement of the atoms within the crystal. But here, we are just showing the atoms with black spots, okay? This is just representation. This is the more or less the real case. This is the just representation. So we consider that we have a crystal, and within this crystal, the atoms are periodically arranged in parallel planes. Here we have one plane of atoms. Here we have another plane of atoms. And the distance between these atomic planes is given with d. This is the distance between the atomic planes. And now we send an X-ray beam. Let me draw an X-ray source here. Let's consider that here we have an X-ray source. And here let's consider we have an X-ray detector. Okay? So we send X-rays to the crystal, to the sample here. But we have some conditions. What kind of X-rays we send? We consider that the incoming X-ray beam consists of monochromatic wavelength. What is the meaning of monochromatic wavelength? We have just single wavelength here. We are using, let's say here, copper K alpha radiation, and we send X-rays with some certain wavelengths. Each incoming X-ray has the same wavelength, okay? And another condition, they are parallel to each other. So this X-ray here coming to this surface, this X-ray here coming to this surface, and other X-rays within the X-ray beam are parallel to each other. Then what happens in atomic scale? We have discussed the absorption and scattering mechanisms in the previous lectures. So here we have hard X-rays. In X-ray diffraction experiments, we use hard X-rays, and you can expect that the scattering mechanisms will be dominant within the X-ray matter interaction, okay? So there will be scattering here. So this incoming X-rays will be scattered everywhere from the atoms with the interaction of X-rays and electrons within the atoms, okay? So we will have many scattered X-rays. This is here theta, incident angle, the angle between the X-ray and sample surface or surface of the atomic plane, and these are the diffracted X-rays, okay? But in addition to this diffracted X-rays, we have many scattered X-rays, okay? So in diffraction experiment, we are mainly concentrating on this diffracted parts, but don't forget, this is just representation. We have many X-rays scattered to everywhere. So this is the wavelength of the incoming X-ray beam, and this is the interplanar distance. So now let's discuss what will happen within this interaction between X-ray beam and crystal and the atoms within the crystal. So, as I told you, incoming X-rays on the crystal are scattered from atoms in all directions. It is okay. And this part is very important. The scattered X-rays in some directions are exactly in phase and reinforce each other. This is called as constructive interference, and within the forthcoming transparency, I will discuss this issue, and this is the basis of the X-ray diffraction. And what is the definition of a diffracted beam? Diffracted beam can be considered or defined as a beam made up of many scattered X-rays that reinforce each other. Here we have a detector and we have many X-rays scattered in all directions, but I am dealing with the scattered X-rays in phase in the same direction where the detector is waiting, okay? So if this scattered X-rays in this direction are in phase, then they reinforce each other and we have a signal in the detector. Okay, we will discuss the constructive and destructive interference and very general definition of the diffraction. Diffraction is a scattering event, okay? We are just considering the special part of the scattered X-rays and which gives us the diffracted beam. Do you have any question?
Yes, I just have a question about the intensities of that diffracted wave. Is it the same of the incident one or smaller?
No, here we have intensity I0. Here we have a completely different intensity, and this intensity comes to detector will be much lower than the initial intensity. Why? Because many of the incoming X-rays scattered everywhere, okay? Some of them are absorbed within the material, okay? And they go into the different directions. So a very small portion of the incident X-rays are coming to the detector. For this reason, the intensity read by detector is much lower than the incident intensity.
Okay, I got it. Thanks.
Okay, never mind. So then let me continue with constructive and destructive interference. Here I have mentioned that for the diffraction condition, we need a constructive interference. So what is constructive interference? Maybe you already know from the optics lectures, but I would like to repeat it here. Here we have one photon, one electromagnetic radiation, one X-ray, let's say, and here we have another X-ray, and both of them have same wavelength and same amplitude. This is the amplitude of the wave, and this is the wavelength of the wave, okay? From the crest to crest, from the trough to trough, we have wavelength. Or you can measure wavelength like this, from this point to this one. So this is also the wavelength. So if they are in phase, then what will happen? They will reinforce each other. So what you see here, the wavelength is same, but the amplitude is twice now, okay? Here we have amplitude A, here we have amplitude A, and they have same wavelengths, and now they have bigger amplitude and same wavelength after superposition of these two waves, okay? This is the constructive interference. They reinforce each other. What do you see here? The amplitude for the crest and for the troughs much bigger compared to the initial case. So this is the constructive interference, and this wave goes to detector, and detector can read a signal, okay? So here detector is waiting. If these two X-rays, or if incoming many X-rays are in phase, then we will read here an intensity. But in second case, let's consider that these two waves are not in phase and there is a phase difference between these two waves. And let's consider here we have phase difference of lambda half. So what do you see here? That look at the initial condition for this wave here, upper wave. We started from this position, and then this is wavelength of the wave. This is the amplitude of the wave, and we have same wavelength and same amplitude here. But what do you see? This wave started here, and this one starts from here. You can consider like this. There is a phase difference between this one and this one, and this phase difference here is given with lambda half. Okay, so what do you see? This crest cancels this trough. This trough cancels this crest. This crest cancels this trough. This trough cancels this crest. So finally, what we have nothing, okay? They cancel each other and detector cannot read something, okay? For the diffraction condition, we need constructive interference. And this constructive interference does not occur every time. It depends on some special conditions which we will discuss within this lecture. Okay, now let's continue with the Bragg's law. So here I have shown you schematic representation of X-ray matter interaction in a perfect crystal. Here I have another schematic representation. Just consider this is incident X-ray, this is another incident X-ray, and this is one atomic plane of the crystal. This is the second atomic plane of the crystal, and they are perfectly parallel to each other, and the distance between the atomic planes is d. In reality, it looks like this. Here we have atoms with some certain radius. Here we have another plane of atoms. Okay, let me try to draw three-dimensionally. So let's consider that this is top view of this plane, and here we have the second plane of the atoms. The distance between two atoms is given with lattice parameter A, okay? And this lattice parameter changes depending on the crystal. And here we have one plane of atoms and another plane of atoms, and distance between these two planes is given with d, interplanar distance, which is also given here. Okay, here we have one atomic plane, here we have another atomic plane, and then this is the X-ray source, these are the incoming X-rays, and this is the scattered plane wave, diffracted X-rays. This is the angle between the incoming X-ray beam and sample plane or atomic plane or sample surface, let's say. And this is the d interplanar distance. So what do you see here? We have two X-rays here, and they are coming together until that point. You see, until that point, they have same path. So starting from this point, this X-ray and this X-ray have also same path. But here between A to C, this second X-ray has more path compared to this upper one, okay? So there is a path difference between two X-rays. This path difference is given with this one. Let's consider that this delta is the path difference, and it can be written like this, AB plus BC, right? So what is AB? What is BC? Here we know that this distance between two planes is given with D, interplanar distance. And here we have theta angle. From the geometry, you know that this is also theta angle. And here we have d sinus theta. And here we have d sinus theta. So then this delta path difference can be written d sinus theta plus d sinus theta. And finally, we have delta is given with 2d sinus theta. This is the path difference between two X-rays. Okay? Any question here?
No, it's clear.
Okay. So there is a path difference, and this path difference can produce one of these conditions, constructive interference or destructive interference. So at the detector, in order to see intensity, we need constructive interference. And for the constructive interference, this path difference given here must be exactly multiples of the wavelength, n times lambda. N is 1, 2, 3, okay? In order to get constructive interference, this path difference between two waves must be equal to the n lambda. So then this is the Bragg's law, and lambda path difference is equal to the path difference to the sinus theta. Is it clear?
Yes, clear.
This is the diffraction condition. If the path difference is different from n lambda, then you cannot see constructive interference at the detector, and this two X-rays or many X-rays coming from the material and goes to the detector will produce destructive interference, and you will not able to see intensity at the detector. Intensity will be 0. And in order to get certain intensity at the detector, then we should have constructive interference, and this is the condition for the diffraction. Now, let me go into a little bit detail. So we have already discussed that this n is positive integer. 1, 2, 3 goes positive number, okay? And it cannot be 1/2. It cannot be 3/2, okay? Otherwise, you will see destructive interference due to the cancellation of crests and troughs in the superposition of two X-rays or many X-rays. Here we have lambda on the left side. This is the wavelength of the incoming X-rays. And here on the right side we have d. This is the interplanar distance. And on the right side we have theta. This is the incident angle, the angle between X-ray beam and sample surface. So now let me discuss another important point related to this Bragg's law. Diffraction occurs only when the wavelength of the incident X-ray is on the order of interplanar distance. So here we have wavelength, incident wavelength, and here we have d, interplanar distance. So what is the interplanar distance within the crystals? It is around 5 angstrom, okay? Let's say 2 angstrom, 2 angstrom, something like this. Depends on the material, depends on the structure. And what about the wavelength of the incoming X-rays? Wavelength of the incoming X-rays can vary in a broad range, but for the diffraction experiments, we, for example, usually use copper K alpha radiation, and this has wavelength of 1.54 angstrom, okay? So what do you see? 1.54 angstrom, and here we have the range, the distance between 1 angstrom and 2 angstrom, something like this. So what we say here, diffraction occurs only when the wavelength of the incident X-ray is on the order of the interplanar distances. So in order to see diffraction, you have to use proper X-ray source, okay, with proper wavelength. Why? It comes from the Bragg's law. If you write Bragg's law like this was the Bragg's law, and just write Bragg's law in this form, and lambda over 2d is equal to sinus theta, right? So what is the maximum value of sinus theta? It can be 1. So this relation must be smaller than 1. So just try to write here, and lambda smaller than 2d, right? For the Bragg condition. What do you see here? N lambda must be less than 2D. So they must be around the same range. For this reason, we are using the wavelengths of incoming X-rays with this wavelengths, 1.54 or around this angstroms. Any question here?
No, clear.
Okay, then let's try to discuss the Bragg condition. Here, I will repeat your old information from the solid-state physics courses. Maybe you remember, maybe you have forgotten, but let me remind you here. In the solid-state physics courses, we have learned scattering vector, K, okay? In some books, you may see it Q, capital Q, okay? So sometimes this symbol is also used for scattering vector. And we have another term in solid-state physics courses, reciprocal lattice vector, G, okay? So the scattering vector K is given with this expression, 4 pi over lambda sinus theta and n unit vector. This shows the direction of this scattering vector. And reciprocal lattice vector is given with this expression, 2d over dHKL, and this is the unit vector, shows the direction. What is d? D is the interplanar distance. This is d. What is HKL? These are the Miller indices. You have also learned in solid-state physics courses. Within the next lecture, I will remind you some parts of this information. So dHKL, interplanar distance, depends on the surfaces, okay? For example, if you have 1, 0, 0 surface, then you will have different D. If you have 1, 1, 1 surface, then you will have different D. So for this reason, we show it with dHKL, okay? I will go into detail during the next lecture. So let me clean this part and then continue to discuss the scattering vector and reciprocal lattice vector. So scattering vector is given with this expression and reciprocal lattice vector is given with this expression. For the Bragg condition, in order to observe diffraction, we should have this condition. Scattering vector must be equal to the reciprocal lattice vector. So just try to write this expression. Instead of K, just use this one, 4 pi over lambda sinus theta. Instead of reciprocal lattice vector, just use this expression. What do you see here? This is the Bragg condition for n is equal to 1, okay? This is the Bragg condition. If the scattering vector is equal to the reciprocal lattice vector, then diffraction is possible. So let me remind you how to get this expression. We have K initial here. What is K? Propagation vector for the wave, okay? Let's consider X-ray is coming with some certain angle to the surface of the crystal, and then it is diffracted, it is reflected with same angle, theta angle. Okay, so then these two vectors, K initial, propagation vector of incident wave, and this K final is propagation vector of reflected or diffracted or scattered photon. Okay, then this K here, resultant vector, gives us the scattering vector. So how this K is equal to this expression? This K initial, you know from the other physics courses that K is given 2 pi over lambda, right? This is the magnitude of K. So look at this K. This vector here has two components. And this one, has also two components, or you can show it here. This one has two components. So if you take the perpendicular component of this initial k vector, and if you take the perpendicular component of this k final vector, then this k will be 4 pi over lambda sinus theta. Here we have theta. This will be 2 pi over lambda sinus theta. And you will have another one from the k final. Then finally scattering vector can be written like this. Okay, now let me continue with the interplanar distance. Here we have discussed the interplanar distance, and I have told you that it depends on the crystal, it depends on the material. In addition, it depends on the surface for the same crystal materials. So how to define this DHKL? For the cubic crystals, it is written like this. 1 over d square HKL is equal to, maybe you already remember this formula, h square plus k square plus L square, HKL numbers, over A square, square of the lattice parameter. Or you can simply write it like this. This is the system: cubic, tetragonal, orthorhombic, hexagonal, monoclinic, triclinic, and this is the interplanar distance. For example, for the tetragonal, you can write like this one, HKL, h square plus k square over a square plus L square C square. Okay, for tetragonal. For the orthorhombic, we have different. For hexagonal, we have different. Okay, for monoclinic, we have different. I strongly suggest you to keep in your mind at least this one for the cubic structures, interplanar distance. So within the next lecture, I will go into detail a little bit with the Miller indices and interplanar distance for different surfaces within the crystal. Now let me discuss the structure factor. It is also very important in X-ray diffraction experiments and calculations. It is also discussed in solid-state physics books, in solid-state physics courses in detail. So what is the structure factor and what is its importance for the diffraction? The symbol is FHKL. As you understand, it also depends on the Miller indices. It depends on the surface of the crystal, okay? So what is the importance of this structure factor? The structure factor determines from which planes of a crystal diffraction can be observed and from which planes diffraction cannot be observed. Let me explain like this. Let me draw a crystal here. Let's consider this is a cubic crystal. And now I am sending X-ray to this surface. Let's consider we have many parallel planes within this crystal. And let's consider the name of the surface is 001, let's say. Okay, so now I send X-rays to this surface. This is 111 surface. I will go into detail in next lecture. Okay, you send X-rays to this surface with some theta angle. Okay, we have many of these surfaces which are parallel to each other, let's say. Okay, so what is the diffraction from this surface? This is 111 surface for the cubic structure. Okay, so depending on the surface within the same crystal, this structure factor changes. And if the structure factor is 0, you cannot see any diffraction. If the structure factor is different from 0, you can see diffraction. Why? Because depending on the surface, the interplanar distance here, let's consider that this is the interplanar distance for 111 surface, and this is the interplanar distance 001 surface, okay? So depending on the interplanar distance for different surfaces, the phase difference between the X-rays scattered from the atoms can be lambda half. Then they destroy, they cancel each other, and you cannot see any diffraction, okay? And sometimes, depending on the surface, you can produce constructive interference and you can observe diffraction. So I will discuss these conditions within this part. Here, we have already discussed constructive interference, destructive interference. So as I have discussed, depending on the interplanar distance for different surfaces within the same crystal, you can observe constructive interference or destructive interference. So then if you have destructive interference, then structure factor of this surface is 0, okay? This mechanism is discussed in detail in solid-state physics courses. For this reason, I will not go into detail. I will just give you the results for some structures. Here I will discuss two conditions. One is structure factor for body-centered cubic structure, BCC. The other one is structure factor for face-centered cubic structure, FCC. So what about the structure factor F for BCC crystals? If the structure is BCC, then if the sum of HKL numbers is even number, then we have certain structure factor. For example, for the cubic BCC structure, I can give you some numbers, some surfaces, for example, 2, 2, 0. The sum of HKL numbers is even. Look at this surface, 2, 2, 2. Or look at this surface, 2, 1, 1, let's say, okay? Or 0, 2. So the sum of HKL numbers is even for all these surfaces, okay? But if the sum of HKL numbers is odd, then we have 0 structure factor. You cannot observe diffraction from these surfaces of BCC structures. It is not allowed, okay? So other example, 1, 1, 1. You cannot observe diffraction from this surface of BCC structure, okay? Or 2, 1, 0. You cannot observe diffraction from this surface, something like this. But if the crystal structure is FCC, face-centered cubic, then we have different relations for the structure factor. Structure factor is different from 0 if the all HKL numbers here are even or all of them are odd. For example, 1, 1, 1 for the FCC, 2, 0, 0 for FCC, 2, 2, 0 for FCC. We have even, even, even. We have even, even, even. We have odd, odd, odd numbers, okay? So then you can see diffraction from these surfaces. But if HKL numbers are mixed, odd, even, even, odd, even, odd, odd, even, okay, you cannot observe any diffraction from these surfaces of FCC structures, okay? So for different structures, we have different structure factors, and you must be careful. For example, we have iron. Iron has BCC structure at room temperature. For example, nickel in periodic table has FCC structure at room temperature. Okay, so if you are dealing with nickel, if you are measuring nickel, and if you would like to get diffraction patterns from the nickel, and if you are looking for 100 surface, you cannot observe this diffraction, okay? So you spend your time, but you will not able to see something. You have to look for these surfaces because diffraction allowed from these surfaces of FCC nickel. If you are dealing with iron and if you are carrying out X-ray diffraction with iron, you have to deal with these surfaces of iron. You cannot observe diffraction peaks from these surfaces of iron. Any question here?
No, it's clear.
So this was the basic information about the X-ray diffraction, and now I will give you information about three main diffraction methods used in the scientific experiments usually, okay? Of course, it is not limited with these experiments, but these are the common ones. Let me start with the Laue method. You remember that experiment which I have explained at the beginning of my talk. Here we have an X-ray source. X-rays are coming with some certain fixed theta angle, okay? This is the incident angle of the X-rays. This is the crystal here under investigation. And then here we have a film, photographic film, or it can be digital detector. We have discussed many types of detectors, okay? CCD detectors, many other detectors we have discussed in previous lectures. So here you have a detector. Here we have X-ray source, but in case of Laue method, we have continuous spectrum, okay? We are using white light. What is the meaning of white light? It is continuous spectrum. It contains many wavelengths, okay? It is not a monochromatic X-ray source. It is continuous spectrum, and then we have many wavelengths within this X-ray beam. Incident angle theta is fixed, okay? Then each plane within this crystal chooses a different wavelength to accommodate Bragg's law. So look at this relation. We have theta, we have d. What is d? Interplanar distance. And within this crystal, there are many different surfaces. As I have discussed in the previous transparencies, 100 surface, 1110 surface, 200 surface, 222 surface, okay? There are many different surfaces, and depending on the surface, we have different interplanar distance, DHKL, okay? So each interplanar distance, each surface within this crystal chooses different wavelength of the light from the incoming beam, and they are diffracted like this, okay? Each plane in the crystal chooses a different wavelength to accommodate Bragg's law. Each diffracted beam has a different wavelength. So the crystal surfaces selects different wavelengths, but it should accommodate Bragg's law and then diffract it from the crystal to the different angles. Any question here? This is the Laue method, and very common one, I should say the most common one, theta to theta scan or theta to theta measurement. So what we have here, we have a fixed monochromatic wavelength, we have single wavelength X-ray source, and we change theta to theta together, okay? Let me draw the experimental condition here. Let's consider this is the thin film or crystal, and X-ray is coming with some certain theta angle. This is the X-ray source, and it is diffracted from the crystal, let's say, or thin film, and it goes to the detector. This is monochromatic X-ray source. We have certain single wavelength, okay? Then what is theta, what is 2 theta? Theta is this one, the angle between incident X-ray beam and the sample surface. This is theta. This is also called as sample angle. What is 2 theta here? 2 theta is this one. Look at this one. This incoming X-ray has this type of projection. Okay, so here I have another theta. Then here I have 2 theta. What is this? The angle between the incoming X-ray beam and the detector position. This is the 2 theta. And usually this 2 theta angle is called as detector angle. So what is theta, 2 theta scan? In this type of experiments, this X-ray source, let me choose another color, or let me draw here. This is the sample. This is the X-ray beam, comes with some certain angle, and this is the X-ray source. And detector is here. And this is the theta, or this is the 2 theta. Okay? So in theta, 2 theta scan, theta, 2 theta experiments, this X-ray source moves in this direction and detector also moves in this direction. And we always should have this relation, okay? And if you move the X-ray source in this direction, you have to move the detector in that direction to accommodate this condition. Of course, in some laboratory X-ray sources, you can move X-ray source, but in synchrotron light sources, the position of the beam line and the position of the X-ray source is fixed. Then, instead of moving X-ray source, you can move the sample here. Okay? Then if you move the sample, then you can change the angle between the incoming X-ray and sample surface, and detector position is also changed. So this is the theta, 2 theta scan, and very common in X-ray diffraction experiments. Any question here?
No.
This is my last transparency today. I will finish with theta scan. As you may understand from the name, in theta scan, we change the position of the sample. We change the angle between sample surface and X-ray beam. We have monochromatic incoming X-ray beam, and the position of the detector is fixed. Lambda wavelength is fixed, and position of the detector is fixed, and we change the sample angle, or we change the theta angle. So how to carry out this type of experiments? Here we have sample. Here we have detector. This is theta. Let's say this is the initial incident angle of the X-ray beam, and this is the 2 theta. Detector is fixed. Detector is waiting always here at fixed 2 theta position, but you change the sample angle, okay? You move the sample in this direction or in this direction, okay? Then you change the incident angle, theta angle. This is the X-ray source here. The position of the, let's say, X-ray source is fixed, and you change the sample angle. Or in some X-ray diffraction machines, instruments, the sample position here is fixed, detector position is fixed, and X-ray source is moved in either directions. Okay, then you can also change the theta angle. So this is called as theta scan. So this type of experiments are very important to check the roughness and inhomogeneities within the sample. And this one, this theta, 2 theta scan, is very general form of X-ray diffraction experiments, and by using this method, you can determine the Miller indices of the crystals, you can determine the defects in the crystals, you can determine the lattice parameter interplanar distance within the crystals. And next lecture, we will continue with the applications of this X-ray diffraction, and I will show you some real data taken with X-ray diffraction method. Then with this transparency, I finish my lecture. So see you next week. Take care of yourself.